Good morning to all of you.
Good morning, sir.
Yeah, good
Good
morning.
morning, sir.
Good morning. So, are there any questions, doubts? Anybody?
Hello, sir.
Yeah,
Sir, in the last class, we derived the matrix C, in which A and D are the diagonal element.
yeah. Not diagonal. They are each is a
Order.
3 by 3.
With A and D are the matrix
Yeah, they are matrix 3 by 3. Yeah,
3 by 3. So because A is only in a plane like a membrane matrix, and D for the bending.
yeah,
But and the off diagonal element are zero due to the integration minus h by 2 to h by 2. But
yeah.
if the thickness direction z if discontinued over the minus h by 2 to 0 and 0 to h by 2, then the off diagonal element will not be 0. So
Yeah, so
then
if the property, yeah, if the material distribution is not symmetric about z equal to 0 plane, then
yes, sir.
those half diagonal matrices will also be non-zero. They are coupling matrices. Usually we call B, bending extension coupling stiffness coefficient matrix.
It is like ABD matrix for the composite, right?
Yeah, right. Yeah, for similar to ABD matrix for composites. Yes.
Okay.
Yeah. Any other question? Anybody? Okay, so if there are no questions, so let me start. So I am continue today. I am going to discuss actually hyperelasticity, a little bit on hyperelasticity. Of course, it's actually a vast topic, but with the whatever time we have, I will only be able to give some kind of introduction. So it is not writing. Is my screen visible? Hello, is my screen visible?
It's visible, sir.
Okay. Yeah, so I'm going to continue with the finite deformation. So in that I'm going to talk about, of course, for other different types of elements, you should be able to develop the element level governing equation and incremental form depending on the problem and kind of nonlinearity. So I have just given 3 examples. So finite deformation, today I am going to discuss hyperelasticity. So in this there are both material as well as geometric nonlinearity. So material is elastic nonlinear and there is a geometric nonlinearity. So both are there, material nonlinearity, material and geometric nonlinearity.
Sir, previous one is only geometric nonlinearity.
Yeah, previous one was only geometric nonlinearity. So in this we are going to consider both material nonlinearity and geometric nonlinearity. Material is of course elastic nonlinear. So we need in hyperelasticity most of the time we end up actually assuming a form for strain energy density function and then express stresses and the constitutive matrix in terms of derivatives of that. So that requires the use of actually second law of thermodynamics. So let me little bit discuss on that and then move on to hyperelasticity. So little bit on thermodynamics. So I'm briefly going to talk of first law. So you know the first law of thermodynamics. I'm going to write here in the red form. So the first law says that rate form means U dot is equal to the work done by the stresses. So let us say that is S transpose into E dot, or E dot transpose into S, any form you can write, and minus the heat flowing out of the system. So here U dot is, if you look at, is the rate of change of internal energy of the system, per unit volume. So it is more or less similar to what you would have learned in basic thermodynamics course. So then here S, this already, S transpose into E dot is power of stresses, because we are taking the strain rate. So S transpose into E dot will give us power of stresses. So you can say it is basically work stored in the system. And this del dot Q, Q is a vector, the heat flow vector. So Q, del dot Q is heat flow out of the system, heat flow rate out of the system. Again, of course, this is also per unit volume. So this is the first law of thermodynamics. So already it is like internal energy is equal to work done minus the heat going out of the system. So in rate form it is written U dot is equal to S transpose E dot minus delta Q. And here work is the power is of stresses. So that's the kind rate of work. So that is power. And the second law of thermodynamics is written as in the rate form. So eta dot plus del dot Q, the heat going out of the system, into divided by T, must be greater than equal to 0.
Hello, sir.
So
Sir,
yeah,
power of stress is also per unit volume.
yeah, that is also, yes, per unit volume. Yeah, that's also per unit volume. So let me put it as that. When you write S into E dot, so obviously that is per unit volume. So let me write here, okay, per unit volume. So in second law is in this form, where this eta dot is rate of change of entropy of the system per unit volume. Entropy of the system per unit volume. And del dot Q we have already defined in the first law, and this T is absolute temperature. So now we want to, yeah.
Sir, in first law, are we taking the work done on the system as positive, or?
Yeah, we are taking work done on the system as positive. So you see the strain energy is kind of coming from the work done by the forces on the system, which is stored in the form of strain energy. So this is rate of change of strain energy per unit volume minus heat loss from the system would be net increase in the internal energy of the system. And if there is no heat loss, then the net internal energy of the system is equal to strain energy stored in the system. So that is how you look at the first law.
Okay. So sir, here
Yes.
U dot is basically the rate change, like.
Yeah, rate of change
Not
of
the-
internal energy.
Okay.
All are rate form,
Okay.
no U dot, then here E dot is there, and Q is a heat flow rate. So del dot Q is the heat flow out of the system per unit volume.
Okay, sir.
Hello,
Yeah.
sir. Sir, in
Yeah.
strain energy, we are writing half into stress into strain.
Yeah, but here when we are writing the power, it is simply S transpose into E dot, Sij into Eij dot.
We are excluding half.
No, half will not come. Half comes when we, for linear elastic case, when we integrate it, so then half comes.
Okay, sir. Okay.
So integration, no, this is rate of change. So we integrate it. When we integrate, then you get half. For linear, of course, for linear elastic. So now what we want to do is we want to substitute the expression for delta Q from the first law into the second law, and then we want to assume now the internal energy as function of state variables, and then from there we want to deduce some relationship between the basically the rate of change of internal energy with respect to entropy as temperature, rate of change of internal energy with respect to strain as stress tensor, and things like that. So again, from first law, we can say, no, we have already written u dot, no, yeah, you can write in that index notation also. So you can say Sij into Eij. So the repeated index here implies summation minus del dot q. So you can say that del dot q is equal to Sij into Eij dot minus u dot. So that's what you can write. And then from second law, if you substitute this, so second law we have this eta dot remains as it is, and in place of del dot q we have this Sij Eij dot minus u dot divided by t. This is greater than equal to 0. So this is the second law. We have written delta q in terms of power of stresses and rate of change of internal energy, that is u dot, and this is Eij dot here. So now if you multiply the whole expression by t, so you can write t into eta dot plus Sij into Eij dot minus u dot. This is greater than equal to 0. So now we have, if we look at the internal energy, so internal energy U is function of state variables and internal variables. So that is basically what we are saying in this, is that U is a function of entropy is a state variable, strain is a state variable Eij, and there are internal variables, say like Q alpha. So here Q alpha is a set of internal variables, and these internal variables basically represent strain, hardening, damage, crack density, I mean depending on what kind of system we are considering. So these are internal variables, and they represent like if you have a damage in the material, so even if it is elastic but there is a damage, so that damage would be taken as internal variable. So we have damage, and even if there is a in micro cracks developing in the material, so the crack density, and if it is elastoplasticity, then strain, hardening, and many other variables. There is a list of many variables like this are referred to as internal variables. So now from this, since u is a function of eta, Eij, and q alpha, so if you write u dot, so we can write u dot is equal to rate of change of u with respect to eta into eta dot, that is the entropy term, and then we have rate of change of u with respect to strain, so Eij into Eij dot, and we have rate of change of u with respect to q alpha, del q alpha into q alpha dot. So this is u dot, and here the repeated indices imply summation both. So there is a summation implied in this term also. There is a summation implied in this term also. So here repeated indices implies summation. So now if we put this in the second law again, what we have got now, the second law we have written in this form over here, and in this if we put u dot, so finally you would see that the second law would reduce to, second law is going to reduce to t into eta dot is already there, then we have plus this Sij into Eiz dot is there, and then minus u dot is there, and in place of u dot we are writing del u by del eta into eta dot minus del u by del Eiz into Eiz dot minus del u by del q alpha into q alpha dot, and this is greater than equal to 0, of course. So we can club the similar terms, like this term and these two terms have eta dot, so we can write t minus del u by del eta into eta dot, and similarly then we can combine these two terms, so we can write Sij minus del u upon del Eiz into Eiz dot, so we can combine these terms together, and then we have minus, of course, this del u by del q alpha into q alpha dot greater than equal to 0. So now in this equation, if you see, we have to make sure that sum of all these three terms, we have got this term plus this term plus this term, should be greater than equal to 0. That is as per the thermodynamics. So that is stating that the total internal energy of the system plus surrounding is always increasing. So either increasing or is equal to 0. So this sum of these three terms should be greater than equal to 0. Now individually also we need to look at these terms. So now if you look at this term eta dot, so depending on whether there is a heat flow inside the system or heat flow out of the system, so this eta dot could be positive or negative. So if this term is non-zero, alone, let us say only the eta dot is changing, Eiz dot and q alpha dot are 0, there is no change in the strain, and there is no change in the internal variables, so only it's the entropy which is changing. So if this term is non-zero, so this expression would be positive or negative depending on whether eta dot is positive or negative, so it will not satisfy the inequality. So then what we require, that no, this term must be equal to 0, this term must be equal to 0, and that gives T equal to del U by del eta. So that means absolute temperature is rate of change of internal energy with respect to entropy. So that is one condition we get. Now similarly, let us say there is no change in the entropy, eta is constant, there is no change in the internal variables. Only now this term, in this term Eiz dot is changing. Now Eiz dot could be positive or negative. That means strain could either increase or decrease, because it depends on the system loading or unloading. So the strain may increase or decrease. So now if this term is, let us say, non-zero, so if this term is non-zero, Sij minus del U upon del Eiz, so then this whole term together can also become negative. So then it will not satisfy the inequality. So then we require that Sij must be equal to del U upon del Eiz. So that means if this term is 0, so then you will have basically whether the strain is increasing or decreasing, this term will always be 0. So it will satisfy this inequality what is written over here. And then the last thing which is left out, then now these two terms are 0 because T is equal to del U by del eta we have argued out. Similarly, Sij equal to del U upon del Eiz we argued out. So finally the last term which is left is minus del U upon del Q alpha into Q alpha dot must be greater than equal to actually 0. So now in this, of course, internal variables always increase. So Q alpha dot is always going to be positive. So then what you require is that del U by del Q alpha should be negative. So from this we also imply that del U by del Q alpha must be negative, must be actually negative. And this is since Q alpha dot is always positive.
Sir,
Yeah,
sir, we were able to do other two coefficients as zero because
yeah,
they were the difference of two quantities.
right.
But in this case, there is only one quantity in the coefficient of q dot alpha, so we cannot like make it zero. We will have to
Yeah,
assume
right.
that it should be less than zero.
Yeah, right,
Okay, sir.
right. Yeah,
Hello,
yeah,
sir.
yeah.
This equation in which there are three terms, the summation of all three terms should be equal to zero. Why we are taking individual terms?
So
It should be
yeah,
equal to zero.
some of all the three terms, but the depending on the process, no, in a process there could be a situation where there is only change in the entropy, let us say. So it's only thermal problems. So they change only in entropy. There is no change in the strain. So that possibility is also there. So it should satisfy individually also. If there is only change in entropy, so then also this inequality should be satisfied. If there is only mechanical deformation, there is only change in strain, then also it should be satisfied. And similarly, so ultimately,
Term also, no?
pardon?
If there is only thermal stresses, like only eta dot is there, not
Yeah.
the Ei dot, then the internal variable will play a role, and by combining the first and third term will make it greater than or equal to zero.
No, so we are saying that there is no change in the internal variables. Whatever internal variables, so we are considering three separate possibilities. Where there is only change in entropy, so then also no, this inequality should be satisfied because then Eij dot is zero, Q alpha dot is zero. So then equality should be satisfied whether eta dot is positive or negative. For that you require T equal to del U by del eta. Similarly, there is no change in eta dot, there is no change in Q alpha dot, but there is only change in Eij dot. So then also this inequality should be satisfied, and for the because Eij dot could be positive or negative, so we require for the inequality to be satisfied, we require this term to be zero, and that is how we get to this. And this is what is important relationship we are getting over here, that yeah, so this is the important relation we are getting. So that means stress, the second Piala-Kirchhoff stress tensor can be expressed as gradient of the strain energy density with respect to a green Lagrange strain tensor. So that's the important relation we are getting. So we are arguing out separately also. If there no only eta dot change is there, then also the inequality should be satisfied. If only change in Eij dot, then also this inequality should be satisfied. So that is how we are arguing out. And once we have these two terms zero, so then ultimately we are left with only the last term. And for the last term, then we have this condition that del U by del Q alpha should be negative. Since Q, the internal variables would always increase. So Q alpha dot is going to be always positive. So we need del U by del Q alpha less than zero to satisfy the second law of thermodynamics.
Hello, sir.
So,
Sir,
yeah.
how we are saying that internal variable will always positive, the change in internal
Yeah, so
variable?
let's say if there is a damage is there, so if there is a damage in the material, either damage would increase or it will remain constant, but it will not decrease. The material is not going to repair the damage on its own. Similarly, if there is a plasticity, so there is going to be plastic strain could also be an internal variable, or of course I have not written in that considering all those aspects. But if you look at the equivalent plastic strain, so it will either increase or it will remain constant. It will not go to will
Decrease.
come back, yeah, to zero like that. So that is how we are saying all those kind of variables are put under this.
Okay.
Yeah.
Hello, sir.
Yeah.
Sir, internal energy of the system and strain energy are same.
Yeah, for the say in case of no change in temperature isothermal process, yes, the internal energy would be equal to strain energy. Internal energy per unit volume would be equal to strain energy density.
Okay. Means whole total what we are getting U, we are considering
Yeah.
is strain energy.
Yeah. is internal energy, and for isothermal deformation problem, it is equal to strain energy density. So now, so this is actually why I took that, because I wanted to just show you that we have Sij equal to del U upon del Eij. So this relationship is because in case of hyperelastic materials, we assume the form of strain energy density, and from that we derive the relationship between the stress and strain. So we require this, and that is why I wanted to derive it. So now coming back to again hyperelastic materials. Hyperelastic materials. So I think if you recall, when I had discussed the viscoelasticity, so that time I had talked about materials whether the temperature is less than Tg, approximately equal to Tg, or T is greater than Tg. So if T is less than Tg, so it behaves more like elastic solid. If it is approximately operating temperature is approximately close to glass transition temperature, then it behaves as a viscoelastic material. And if operating temperature is greater than Tg, then it behaves as a hyperelastic material. So the examples of hyperelastic materials are all these polymers, elastomers, etc. So examples are, say, polymers, foam, biological tissues, elastomers. They are basically all types of these polymers. And main thing here is that the operating temperature T is greater than Tg. And if T is greater than Tg, material behaves as hyperelastic. In hyperelastic, hyper means excessive elasticity. So the material remains elastic for large values of strain. So hyperelastic material, elastic material remains elastic, of course non-linear elastic, so remains elastic for large values of strains. So the strain is like can be 100%, say 200%, or 300%. So these are the kind of, even the material remains elastic within these limits. So now the constitutive relation, as I said, rather than assuming that a relationship between, yes.
So, as we are saying, if the material remain elastic, it means their yield strength will increase.
Yeah. So it doesn't yield up to these high strains, no, to 300% strains. It doesn't
The
yield.
yield strength will increase twice or thrice.
Yeah.
Accordingly.
Yeah. So now for these materials, we want to look at, yes.
Well, is it hyperelastic when we'll release the load? It will completely recover, or
Yeah, it will.
some?
Yeah, why it will recover? It will come back to its original state.
Okay, sir.
Yeah. So if you look at the constitutive relation, so rather than talking of directly the relationship between stress and strain, actually strain energy density is assumed, and then the derivative of strain energy density with respect to strain gives the stress. So that is what is done in this. So we have different forms of strain energy density for hyperelastic material. You could find 15 to 20 different models. So obviously I will not be, I will just give one example, and you can look at the literature if you're interested in hyperelasticity. So this is constitutive relation is nonlinear elastic. And the relationship is Sij equal to, like we have written as del U upon del Eij. Now for the isothermal case, U would be equal to strain energy density. So we can write it as del pi by del Eij. So where pi is strain energy density. So here U is equal to pi. Basically, total internal energy is equal to strain energy stored in the body. And now what we do in the hyperelastic model, some of the basic concepts like when I look at the strain energy density, so this pi is expressed as a function of either the right Cauchy green deformation tensor, as a function of either invariance of right Cauchy green deformation tensor or left Cauchy green deformation tensor. So expressed as functions of function of right. So I'm going to talk about right Cauchy green deformation tensor, but in the literature you also find it is expressed in terms of invariance of left Cauchy green deformation tensor. So right Cauchy green deformation tensor C. So that is denoted by actually C. Right. So we have used that notation. So if you remember, we have written this C. No, when we talk of the deformation gradient, we introduced the C. So C was right Cauchy means F transpose F, and left Cauchy green deformation tensor means F into F transpose. So that is known as left Cauchy green deformation tensor. And we have seen that this, of course, can be written in terms of green Lagrange strain tensor as 2E plus I. I is the identity matrix. So the invariants of C are invariants like the second order tensor. So we have invariants. So invariants of C are, one is known as the first invariant I1. So I1 would be C11 plus C22 trace of C. So C11 plus C22 plus C33 is I1, and I2 would be the second invariant. And second invariant means you take 2 by 2 subdeterminants, 3 possible leading subdeterminants. So you get C11 into C22 plus C22 into C33 plus C33 into C11 minus C12 into C21 minus, of course it is symmetric. When you write C as F transpose F, it is symmetric. So C12 would be equal to C21, C23 would be equal to C32, and minus C13 equal to C31. So they all will be same. So you can write C12 square minus C23 square minus. So essentially what we are doing, and I3 is the determinant of this C matrix C. So these are the three invariants of right Cauchy green deformation tensor C, I1, I2 and I3. And now if you look at this can also be actually written as J square. So we have already talked about J. J is the determinant of the deformation gradient. So since C is F transpose F, so determinant of C would be determinant of F transpose into determinant of F, and both would be J, so it would be equal to J square. So we have already defined that determinant of F is equal to J, and this is also of course equal to change of the current volume divided by the reference volume, differential current differential volume divided by reference differential volume. Now if you want to look at the strain energy, so we, rather than directly writing the strain energy in terms of I1, I2, I3, so see, if you look at the C, which is F transpose into F, it has actually two modes of deformation of the body. One is change in the shape of the body, and another is change in the volume. So change in the shape is distortional part, and change in the volume is dilatational part, or the volume change. So usually what we want to do is we want to separate out the distortional part and dilatational part. So we actually write the strain energy as in two parts: distortional strain energy and volumetric strain energy. So the reason will be clear when we talk of nearly incompressible materials, and then there is a volumetric locking. So to handle that, we have to separate out the volumetric term and then do the appropriate reduce integration and things like that. So that is why we need to do this. So what is done is that strain energy is decomposed as Distortional, so distortion means change in shape. Distortional strain energy and volumetric strain energy or dilatational strain energy. Volumetric, and also it is known as dilatational strain energy. So now how do we do that? So for that, what we do is the actually additive, we do the multiplicative decomposition of deformation gradient. So for this decomposition, that is decomposition of strain energy into distortional and volumetric, we do for this decomposition we find the reduced deformation gradient with J bar equal to 0. We find reduced deformation gradient and the determinant of that will be 0. So the determinant of the reduced deformation gradient is written as J, and that is equal to unity. J bar is equal to unity. That means no change in volume, so it's only distortion part. So for this, let us say we have F, the deformation gradient F, that is written as some multiplier into F bar. So in this F, you already know this is the deformation gradient. We already know this deformation gradient, and this is a multiplier, and this F bar is what is known as reduced deformation gradient. So then what we do is, now from this equation you can also say that, see, this F bar is nothing but 1 upon A into F, the deformation gradient. The other, we are writing the relationship in a reverse way. So that, let us say 1 upon A is A dash, so this would be A dash into F. And what does this F does is represents the F bar. If you look at this reduced deformation gradient F bar, this represents change in shape, no change in volume. Represents change in shape, that is distortion, change in shape, no change in volume. So that means determinant of F bar is actually equal to unity. So now we want to derive what is this A dash, because what should be this A dash, so that we have F bar. So as we know, the determinant of F bar is unity. So we have F bar is equal to unity. So I have already said by definition the determinant of F bar should be unity, so that it represents no change in volume. Because if J equal to 1, change in volume is going to be 0. The original and the reference volume, they would be same. So F bar is A dash into F, we have already written. So this determinant should be equal to unity. So from this we can get, now this can be written as, because when you look at the determinant, it is the multiplication of 3 terms. So when A dash gets multiplied with F and then 3 terms of A dash into F, they are multiplied, we would get A in the determinant A dash cube. So we will have A dash cube into determinant of F is equal to unity, and determinant of F is equal to actually J. So you can say that A dash cube is equal to 1 upon J, or you can say A dash is equal to J to the power minus 1 by 3. So that is what you can write. So ultimately you can say that the reduced deformation gradient F bar would be equal to J to the power minus 1 by 3 into F. So this is what is known as the multiplicative decomposition of F. So multiplicative decomposition means, you can also say that F is equal to J to the power 1 by 3 into F bar. So this is the multiplicative decomposition of F. F is written in terms of j to the power half into F bar. So this is the multiplicative decomposition of F. So now in this, if you look at as far as this part is concerned, because this is purely in terms of J. So this represents change in volume. J is representing change in volume, and this is representing change in shape. And of course, I already said that this is multiplicative decomposition. So now once we have this, so we want to now define the, like we have defined the invariants of right Cauchy-Green deformation tensor. So using F bar, we construct reduced Cauchy-Green deformation tensor and then write its reduced its invariants, which are known as reduced invariants. So then next what we do is that is using F bar construct reduced Cauchy-Green deformation tensor. So that is what we do is we write C bar is equal to F bar transpose into F bar. Here there is a F bar. So C bar is equal to F bar transpose into F. So if you want to write it in terms, if you remember, the right Cauchy-Green deformation tensor as a C is equal to F transpose into F. So that's C. Now the invariants of this C bar would be, now if you look at the invariants of C bar, so they will be denoted as I1 bar, I2 bar and I3 bar, and of course I3 bar would be equal to unity because that's the determinant of C bar, and C bar is in terms of F bar and F bar transpose, so their determinants are unity, so I3 bar is going to be unity. And these three are referred to as reduced invariants. Reduced in the sense that we have written the F in terms of j to the power 1 by 3 into F bar, and these are the C bar invariants coming from F bar, that is the reduced deformation gradient. So these are the reduced invariants of C bar. So now if you want to look at, because we know this C bar is equal to F bar transpose into F bar, and F bar is nothing but j to the power minus 1 by 3 into F. So now you can write this as j to the power minus 2 by 3 into F transpose into F. So you can say that this will be j to the power minus 2 by 3 into C. So then you can also write, so once we have this relationship, hello, am I audible? I think no questions in between, so
Yes.
Am I audible?
You are audible, sir.
Okay.
Yes, sir.
So now this C bar is j to the power minus 2 by 3 into C. So if you want to write the relationship between the reduced invariance and invariance of C, so you can look at that I1 bar would be equal to C11 bar plus C22 bar plus C33 bar. That is C11 bar, C22 bar, C33 bar are diagonal elements of a reduced right Cauchy-Green deformation tensor. So since each element of C is j to the power minus 2 by 3 times C, so we can write this as j to the power minus 2 by 3 into I1. So each element know that C11 bar can be written as j to the power minus 2 by 3 into C11. Similarly, C22 bar and C33 bar. So we will get I1 bar as j to the power minus 2 by 3 into I1. And so here, and we have already defined what is I1. So that you already know. And then if you look at the I2 bar is in terms of now C11 bar into C22 bar plus C22 bar into C33 bar. plus C33 bar into C11 bar minus C12 bar into C21 bar. Of course, it is symmetric. Minus C32 bar 32 bar into C23 bar minus C31 bar into C13 bar. So this can be now each C element of C j to the power minus 2 by 3. So since it is a product, so we will get j to the power minus 4 by 3 into I2. And I2 we have already defined earlier, so it's the same I2. And if you look at, of course, the I3 bar is determinant of the C bar matrix, and which is actually unity. So you can also say, no, yeah.
Hello, sir. Sir,
Yeah,
in invariant of C bar, that I1, I2, I3 is equal to 1 means in that only I3 is equal to 1, I think, or I1, I2 both are 1.
No, only I3 bar is equal to unity.
Yes, that okay.
What I'm writing here is I3 bar is equal to unity. See,
in
I1 bar, yeah, I1 bar is.
you have written. That is
Pardon?
confusing actually. In previous page you are writing I1, I1 bar, I2 bar, I3 bar is equal to 1. Actually that was
So we have
confusing.
said here it means that I1 bar, I2 bar are there and I3 bar is equal to unity. So it is not that all three are equal to unity. So this is separate. No, I1 bar, I have just written invariants of C bar are I1 bar, I2 bar and I3 bar. Out of these three, I3 bar is equal to unity. So it is not that all three are unity. No, you have to interpret this term like that. Yeah. So then we have this as I3 bar. And now if you also want to write, because we know if you look at I3, so I3 is the determinant of F transpose into F, that is determinant of actually C, and we know that this is actually equal to J square. So we can say that J is square root of I3, so I3 to the power half. So we can also write reduce invariants in terms of actually I3. So we can also write I1 bar is actually, we have written I1 bar as j to the power minus 2 by 3 into I1, and j is square root of I3. So we can write I3 to the power minus 1 by 3 into I1. I2 bar we can write I3 to the power minus 2 by 3 into I2. And of course I3 bar, we know that it is actually equal to unity. So now what we do, as I said, in the hyperelastic materials, rather than writing directly the relationship between stress and strain, we postulate the form of strain energy density. And this kind of models for strain energy density is written in terms of the reduced invariants are known as phenomenological models. So it is based on, when we test the material, whatever stress strain response we get. So we want to find a model which fits into that. So we call that model as phenomenological model. So there are some which are based on molecular structure. Those are known as micromechanical models. So what I am talking about is the strain energy density function based on phenomenological model. And phenomenological models. So there are, as I said, about 15 to 20 different models are there, but most widely used is known as the Mooney-Rivlin model. So I'm just writing that. Now, if you're interested in exploring this, you can look at the literature and you can find a number of hyperelastic strain energy density functions. So just to give you the representative form, I am taking the example of this Mooney-Rivlin model. So this is Mooney-Rivlin model, means the strain energy density pi, which is a function of reduced invariant I1 bar reduce invariant I2 bar, and J. So this is written as in two parts, C1 into this I1 bar minus 3. So why I1 bar minus 3? Because I1 bar would be unity when there is no deformation. So the strain energy density should be 0. So that is why this is I1 bar minus 3 plus C2 into I2 bar minus 3. And so these first two terms and are actually the distortional part, and the last one will be the volumetric part. So the volumetric part is written separately. So say the bulk modulus K by 2 into J minus 1 whole square. So this is typically the form of the strain energy density function given by three parameter Mooney-Rivlin model. Material parameters are C1, C2 and K. Yeah.
So can you please explain again C1 into I1 bar y minus 3?
Yeah, now this C1 is different from those C11, C22 and C33. These are the constants. So it is written as C1 into I1 bar minus 3, and minus 3, why it is there? Because when there is no deformation, so the deformation gradient would be actually unity. And so when you look at the invariants, the I1 bar and I2 bar would be actually 3. So we want to subtract this 3 from I1 bar and I2 bar so that when there is no deformation, the strain energy density is 0. So undeformed material means I1 bar would be 3, I2 bar would be 3, J would be equal to unity. So we are writing this relationship such a way that undeformed condition strain energy density is 0. So that is how we are writing C1 into I1 bar minus 3, C2 into I2 bar minus 3, K by 2 into J minus 1 whole square. And these C1 and C1, C2 and K are the material parameters. C1, C2 and K are material parameters. And this will be determined, these material parameters will be determined. So experimentally we say do the uniaxial tensile testing of the material, get the stress versus strain response, and then we fit this model into that, because derivative of this strain energy will give you stress, and then we fit that into the strain energy density and find out C1, C2 and K. So these are the material parameters. If you look at here in the strain energy density, the first two terms, these two terms, so the first two terms are basically distortional strain energy, part of the distortional strain energy, distortional strain energy, and the last term, which is K by 2 into J minus 1 whole square, last term is volumetric or dilatational strain energy. Volumetric or dilatational strain energy. So like this, using the reduced invariants, we are able to separate out this strain energy density into two parts: distortional strain energy first two terms and the volumetric strain energy the last term. So we are able to separate out these two parts separately. So we can handle, if we have to carry out reduced integration for volumetric part, so we in all the expressions of stress, constitutive matrix and everywhere we can have that term as separate one, and we can do the reduced integration for that. So now why the last term is volumetric? Yeah.
So can you please explain why if there is no strain, the du by dx is equal to unity?
Why?
Why, sir, when there will be no strain?
Yeah.
Du by dx in that.
No, not du. Yeah, du by dx would be 0.
That one. Then
if you look at F, if you look at F was, we had written, if you remember, identity matrix U into this deformation gradient. We have written as actually
yes,
H.
Yeah, understood. Yes.
So this all the displacement gradients would be 0. So F would be equal to identity. So the C will also be identity. C bar will also be identity. So when we find out the invariant, so I1 bar, I2 bar, they would be, each would be 3.
Yes, sir. Okay. Understood.
And of course, J would be equal to 1.
Yes.
So I was just telling you that, of course, because I1 bar and I2 bar are the reduced invariants, so whatever we write in terms of those are going to be basically the distortional strain energy part, and the last term is the volumetric strain energy. So if you look at, you want to define volumetric strain. So you can define that as in terms of J, and that is nothing but change in the volume in reference configuration divided by the original volume. No, that J is the ratio of that. So I think for that, no, I'm not writing the strain, volumetric strain like that, but we have J equal to dVt by dV naught. So the volumetric strain, if you look at volumetric strain, if you look at it, would be dVt minus dV naught, change in volume upon original volume. So you would see that this is going to be J minus 1. So that is how we are saying the last term is volumetric strain energy. So this is volumetric strain. Now once we have defined the strain energy density, so there are various models. Now I just said you can find up in the literature and the packages, for example, Abacus Census, you will have about 15 to 20 different hyperelastic models depending on the the material you are modeling, the accuracy of stress strain curve you want to represent. You have different models. So now once we have this, so the stress, we know that Sij, second Piola Kirchhoff stress tensor, would be del pi by del Eij. So now you can actually, there are different derivations and different expressions after taking the derivative. So I'm not going into those details. But now if you have to do del pi by del Eij, you can write the derivative of phi with respect to reduced invariance, del pi by del I1 bar into the I1 bar derivative with respect to dij, and del pi by del I2 bar and its derivative with respect to del I2 bar derivative with respect to Eij, and so on. So you can use the chain rule of differentiation, and then you can actually evaluate this expression, because we know that I1 bar, I2 bar, they are in terms of I1 and I2, and I1 and I2 are the invariants of C. And C, we have said at the beginning that here C is in terms of also in terms of 2E plus I. So you can write in terms of actually the elements of Green-Lagrange strain tensor. So you can finally get these derivatives through the chain rule of differentiation. So I'm not going into those details. And similarly, when you look at the constitutive matrix, so Cij KL, the constitutive matrix will be del 2 pi by del Eij del EKL. So that is how you can write the constitutive matrix. So this is the constitutive matrix. And you will see that it is also going to be function of the strain. So it is non-linear. TheCijkl will also be function of a invariance because when you take the derivatives, and so the material is going to be non-linear and it's elastic, of course. So once you have this constitutive relation, so then next thing is the finite element formulation. So the finite element formulation, either you can start with the principle of virtual work, or you can also write the total potential energy functional. So there are both ways you can actually do that. Both of them are going to give you the same element level governing equation and the final incremental form. So if you look at the finite element formulation, so no one is, as I said, from the total potential energy, it is easy to write over here. Total potential energy functional. So we have the form of strain energy density already. So you can write the total potential energy functional I is equal to integration over the reference volume V naught and pi strain energy density, which is a function of I1 bar, I2 bar and J into dV naught. This is the strain energy density per unit volume into dV naught gives you the total strain energy. And then potential of the external forces. This is class. So this is V naught and the potential of the external body forces and surface traction. So you will have U1, U2, U3 transpose into body forces in the reference configuration FB1, FB2, FB3, dV naught, and minus the integration over reference surface Again, u1, u2, u3 are the displacement along x1, x2, x3, and tn1, tn2, tn3 tractions in the referred to reference volume ds naught. So this is the strain energy density, and from this directly now you can get the element level governing equations. So the element level governing equation will come from delta of I equal to 0. So delta of I means pi. You can of course write in different forms, but one possibility is we can write this relationship integration over V naught delta of this is also the principle of actually virtual work. So delta E transpose into S. Delta E is the variation in Green Lagrange strain tensor, into S is the stress tensor. S would be del pi by del E, as you know already I have written, and minus the virtual work of body forces. So delta U1, delta U2, delta U3 into FB. Let me just write as a vector, FB into dV naught minus integration over reference surface delta U1, delta U2, delta U3 into Tn ds not equal to 0. So you can say this is the principle of actually virtual work, where S is nothing but del pi by del E. With respect to each component. So S is derivative of components of S are the derivative of pi with respect to elements of Green Lagrange strain tensor. So you can also write and you can develop the element level governing equation from here. So the development of the element level governing equation is similar to what we discussed for the geometric nonlinearity finite deformation case. So either you come from this or you come from this. Finally, the element level governing equation would be of the same form, B plus BNL coming from the delta of E transpose into, we will have S dV naught minus integration over volume H transpose. These are the interpolation matrix as defined earlier. FB dV naught minus integration over S naught, and then we have this H transpose into Tn ds naught is equal to a null vector. So this is the element level governing equation, and then you can develop the incremental form from this. So that I'm giving you as a homework. So you do that. So this is the element level governing equation, and then you develop the incremental form for based on the Taylor-Sitch expansion for the use of for the application of Newton-Raphson method. So you do yourself. It is similar to what we have been doing already in so many problems. So derive the incremental form. This is your homework. You should do yourself. Yeah, so I think I want to stop here, and I also want to take class tomorrow, so that I can cover because another major topic is contact mechanics. So I have to discuss that also, at least some basics of contact mechanics. So I want to take the lecture tomorrow also, same 11 to 12. So I think I hope you all would be ready to attend that lecture. Is that okay?
Yes, sir.
Hello. So tomorrow also I will take lecture from 11 to 12. So if there are any questions and doubts, you can ask. I want to stop here. Yeah. Any doubts, question? Anybody has any doubt or any question, you can please ask.
Sir, can you please update the due date in the grade scope?
Okay, yeah, I will do that. Okay.
Yes, sir. Thank you.
Okay. If I'm not able to do, you can send through email. I will upload.
Okay, sir. Sure.
Yeah. Are there any other questions, doubts?
Sir, as this is the hyperelasticity problem involve both material nonlinearity and geometric nonlinearity.
Yeah.
So in this case also, should we consider the reference configuration and the current configuration? Like this
Yeah, so
elemental
we
level
are
will be equal?
see, if you look at, we are writing the all, because we are postulating the system energy density per unit original volume. So if you see, all these integrations are with
In
respect
the
to reference volume.
configuration, yes. Yes, sir.
Yeah, reference configuration. Are there any other questions, doubts? So if there are no questions, I am stopping. Thank you all for your attention, and also please attend tomorrow's class.